What's up, Lab Skills Bootcamp? Today we're going to cover quantitative investigational devices. The topics in general that we're going to cover, we'll cover dilutions, dilution factors and the dilution equation, dimensional analysis, buffers, and Henderson-Hasselbalch, the Henderson-Hasselbalch equation. And the reason that we cover these is because all of these items are tools for lab technicians and researchers. Anytime that you want to prepare a buffer or liquid or solid media or serial dilutions for assays, you need to know, just like baking a cake or cooking a recipe, you need to know the ingredients and what ratio of the ingredients you need to use. So some of the buffers that you might prepare are for protein purification, for DNA extraction. You need running buffers and staining and destaining buffers for running gel electrophoresis and analysis like STS-Phage. And also for X-ray crystallography. Some liquid medias are for culture bacteria and tissue culture. Solid media are things like plates. And then serial dilutions with assays are things like flow cytometry and ELISA, Bradford assays. There's a lot of other uses, but these are just a few of them. Okay, so one way we can think about this is we have 5 mils of total solution we want, and we want a 5x dilution. So that will give us 1 mil when we divide it. So what that means is we take 1 mil from our stock solution of our concentrated solution into 4 mils of our diluent or solvent. So an example would be if we were preparing Bradford assay. Bradford is just a reagent. If we wanted a 5-fold dilution of it, and we wanted 5 mils total, we would have 1 mil of the concentrated Bradford reagent into 4 mils of water, which would be the solvent or the diluent. And that would dilute it 5 times. In the second example we have right here, it's still a 5x dilution, but we have 20 mils total. So in this case, we would have 20 mils we still have a 5-fold dilution. So that tells us 4 mils. So what this means is we have 4 mils of the concentrated stock to 16 mils of our diluent or solvent. So taking this 1 to 10, we could also say this is a 10x dilution. And we have a 40 mil total. So we pretty much follow the exact same idea. So we have 40 mils total that we want with a 10-fold dilution. So that's 4 mils again. In this case, we'd have 4 mils of our concentrated stock with 36 mils of our solvent or diluent. Another way you could think about this is if you worked it out as, instead of having 40 mils, if you started with 10 mils, and you wanted to know with the 10x dilution, you'd have 10 mils, a 10x, so you get 1 mil, which would mean 1 mil of your stock and 9 mils of your diluent. And because you have 4 times that amount total, you have 4 times 10, which is 40 mils. If you just take these numbers and multiply by 4, you get the same amount. You get 4 to 36. So it's the same ratio. Another common dilution factor is 3 to 100. And this is a bit more common for flow cytometry than other techniques. It follows the same general idea. It's a bit different. In the case of 3 to 100, if let's say that we wanted 100 mils of total solution, In this case, we would take 3 mils of our concentrated stock, and we would dilute it in 97 mils of whatever solvent we were using. So in this case, you're not dividing like we did up here, but it still is rather intuitive to look at it. In the case of wanting 200 mils total, and it's the same idea as right here. We would just take this and multiply by 2. And in this case, we would get 6 mils. So 194 mils of whatever your solvent would be. And then 1/500, or you could say this is 500x. This is more common in things like serial dilutions, which are very important, especially in assays, like ELISA assays. Anytime, often when you're measuring some concentrations, even protein concentrations, this can be a very important technique. Technically, to be very precise, what this implies is that you would have 1 mil of your concentrated to 499 mils of your solvent, but because you're at 500x, 499 is so large compared to 1 mil. It's practically the same thing if you did 1 mil to 500. Sorry guys, I can't write very well. To 500 mils of your solvent. Practically, it's not going to make a difference. Even though in theory and principle, it is, 500 is a different number than 499. Because the difference in numbers is so large, it doesn't make a practical difference. So we've already touched on calling dilution factors as folds, as you guys can see up here. So a very common fold dilution is a 2-fold or 2x. And it's sort of important before we even talk about a 2x. What is a 1x dilution? What is a 1-fold? So by definition, a 1-fold dilution is no dilution. When you divide 1 by 1, you get 1. So that means that you're adding 1 mil of your stock or your concentrated to nothing. So by definition, a 1x means that you're not diluting at all. So a 2x, in this case, let's say that you had 10 mils total, and you divide by 2, you get 5 mils. So in this case, we have 5 mils of our stock to 5 mils of our solvent. So it just means that you dilute it in half, or by half, depending on how you want to say it. Both conventions are fine. But 2x and 1x can sometimes trip people up. So it's important to distinguish the difference that a 1x dilution means no dilution, and a 2x means that you dilute it by half. People just starting out in the lab without any experience, it's very understandable to think that a 1x means that you're diluting it by half, but that's not the case. And then, we already touched on a 10-fold, a 10x dilution. So if we had 10 mils total, and we were using a 10-fold dilution, we would get 1 mil, which means 1 mil of our concentrated and 9 mils of our diluent. So that brings us to serial dilutions. A serial dilution is a dilution many times, which seems obvious given the name. So the way that you do it practically is you start with a stock. So this is your stock. This is your concentrated solution. And what you would do is you keep a common ratio. So in this case we have 10 mils total, because 1 plus 9 gives you 10. And we keep that convention going all the way through from start to end. Every single one of these you take 1 ml to 9 mils, 1 ml to 9 mils, 1 ml to 9 mils. So the first dilution here is you take 1 ml of your stock into 9 mils of your first dilution, or it would be solvent basically. So let's just say that we've got 1 ml of a buffer, and we're going to dilute it 10x, because this is a 10x dilution, one time. So we're going to add it to 9 mils of water. So that's our first dilution, which would be a 10x dilution. So let me just erase some of this to clean it up a bit. So in this first dilution, going from here to here, this is a 10x dilution. And this is what it tells us here. That basically just means 10x. So then when we go to our second dilution, when we go from here to here, this is another 10x dilution. But it's a 10x dilution of, let's number these. Let's call this 1, 2, 3, 4, and 5. So going from tube 2 to tube 3 is another 10x dilution, but it's a 10x dilution of tube 2. And the same thing for going from tube 3 into tube 4. This is another 10x dilution, because you're diluting tube 3 10 times when you take 1 ml of it into 9 mils of water in tube 4. And when you go from tube 4 to tube 5, you have another 10x dilution. And you're diluting, in this case, you're diluting tube 4 10 times when you take 1 ml of tube 4 and take it into 9 mils of tube 5. So, there's a couple of things that you can take from this. One way to look at this is every time that you dilute, when you go from 1 to 2 to 3 to 4 to 5, so each time you move it, you're diluting. Hold on one second. You're diluting it by a factor of 10 to the negative 1 every single time. Let's make this a bit cleaner. So every time, this is 10 to the negative 1, this is 10 to the negative 1, oops. This is another 10 to the negative 1, 10 to the negative 1. So each time that you dilute, it gets diluted by a factor of 10 to the negative 1, or 10x. These mean the same thing. If you want to find out going from tube 1 all... And if you want to figure out what is the dilution factor going from tube 1 all the way to tube 5, there's two ways that we can go about this. One is we can multiply each of these together. So every single time that we've diluted how many times? How many times have we transferred into a new tube? Well, there's 1, 2, 3, 4. So we multiply 10 by 10 by 10 by 10. And in this case, 10x times, well, let's just call it 10. If we do 10 by 10 by 10 by 10, that's the dilution going from tube 1 to tube 5, is 10,000-fold. Another way that you can look at it instead of talking about it as 10x is using the convention of 10 to the negative 1. So the way that you would do a serial dilution practically in the lab, because we just covered, sort of a more theory-based approach. In tubes 2 5, so 2, 3, 4, and 5, you could pipe it in 9 mils of your solvent. So if it's water in each single one, you're going to pipe at 9 mils. And you're going to have your stock in tube 1 already prepared. What you would do to perform serial dilution is you would pipette 1 mil you would pipette 1 mil from tube 1 straight into tube 2. You'd mix it around so that way it's homogeneous. You can do this with a pipetting technique. You flush your pipette tip in and out while you spin. You sort of stir it around to mix it. At that point, you would discard that tip, get a new pipette tip, and you would pipette another 1 mil from tube 2 into tube 3 and mix it the same way you did in tube 2. So you flush the pipette tip in and out and stir it around simultaneously. You discard that tip, get a new tip, and continue this approach all the way down to tube 5. So that's the practical way to perform serial dilution. Alright guys, that brings us to the dilution equation, and there's two conventions for writing it. There's V1C1 is equal to V2C2, or M1V1 is equal to M2V2. They mean exactly the same thing. V1 is the volume of your stock that you need. So we would write volume of stock needed. C1 is also equal to C2. I'm sorry, to M1. And this is just the concentration of your stock. And by convention, when we use these brackets right here, whatever's inside of it, it means concentration. And V2 is the total volume of your new solution, or your final solution. So you could call it either total or final volume. And C2 is equal to M2. And that's going to be your final concentration. C2 really just means, C means concentration. This equation in general chemistry is most often used with molarity. So M1, M2, they both mean molarity. But you can use them for any type of concentration. It doesn't have to be molarity. It can be percent by volume, percent by mass. You can even use it for dilution factors if you want. So C1, C2, or M1, M2 are for any types of concentration, not just molarity or molality. So working out this example below, that says, suppose you have 3 mils of a stock solution of 100 mg per ml ampicillin, and you'd like to prepare 200 microliters of a 25 per mg per ml solution of ampicillin. So what you do is you basically just assign your variables and then do basic algebraic manipulation. So in this case, we have V1, C1, V2, and C2. So the question is, which variable do we need to find? So we're actually probably better off starting at what we know for sure we have. We know that the final volume of your solution is going to be 200 microliters. So we would assign V2 to be 200 microliters. And we know that the final concentration is going to be 25 mg per ml. And we know that the initial concentration of the stock solution is 100 mg per ml. So what this tells us is that what we need to figure out is how much how much volume of the initial solution do we need to add to, most likely in case of ampicillin it's going to be water, to prepare this solution? So what we don't know is what's the initial volume that we need in order to solve this problem. So we'd set it up like M1 V1 is equal to M2 V2, and we know we're looking for V1. We know that what we want to find is this guy. So we can solve for that by isolating it. And this is the general equation, our final equation that we're going to use is right here. The concentration of the stock is going to be equal to the final concentration times the final volume, all over the initial concentration. So in this case, the final concentration is 25 milligrams per mil. The final volume is 200 microliters. The initial concentration, or the stock solution concentration, is 100 mg per mil. So these units, that should be mil, not microliters. This should be mils. So we know that these units here cancel. So then all I have to do is multiply 25 by 200, and divide by 100. So it'd be easier to just divide by 100, call that 2, and just do 25 times 2. And we know that the volume that we need is going to be 50 microliters. Probably a better way to write this would be to say 50 microliters of let's see, 100 mg per mil ampicillin. Alright, so that brings us to moles and molarity. So moles is just sort of a way of understanding how much of something that you have. So one way to understand this, or to do calculations with it, is just getting straight to the example. So suppose that we wanted to prepare 0.350 moles of sodium chloride. So it's just a dimensional analysis problem. The way that you would set something like this up, you set up what it is that you're looking for. So we have 0.350 moles of sodium chloride. And we know that 1 mole of sodium chloride is 58.44 grams of sodium chloride. So when we multiply this out, these units cancel. You're left with grams of sodium chloride. And the answer for this is just going to be 20.454 grams of sodium chloride. Which brings us to molarity, which is the moles of some substance per liter of solution. So this is often you use molarity when you're preparing a solution, a buffer, a media of some sort. So if someone asks us to prepare a 0.35 molar sodium chloride solution, they're more likely to ask us to prepare it as 350 millimolar solution. These mean the same thing, but that's the convention is to call it a 350 millimolar solution. So, if you recall in the decimal system, if we have something like meter, and we move the decimal place one time, we have decimeter. If we move it again, we have centimeter, and one more time we have millimeter. And we can do the same thing for liter. So if we start out with liters, and we move the decimal once, we have deciliters. If we move it twice, we have centiliters, and the third time we have milliliters. And let's go ahead and just clean this up a little bit. So if someone asks us to prepare a 150 millimolar sodium chloride solution, something like that, and what they want to know is they want 1 liter of 150 millimolar solution. How many grams of sodium chloride do we need to dissolve? So we could write 150 millimolar sodium chloride and we know that it takes 1,000 millimoles to make up 1 mole. And 1 mole of sodium chloride has 58.44 grams of sodium chloride. So then these cancel. And we get 8.766. So that's the mass of sodium chloride that we would have to measure out to dissolve to prepare a solution that contained 150 millimolar sodium chloride in 1 liter of solution. It's also important to mention when you prepare a solution, usually, in this case, if we were preparing 1 liter, you would fill a beaker, or you can even do this in a cylinder because you know that the sodium chloride will dissolve readily at room temperature. With about, in this case, 950 mils of water, and you would pretty much just assume that the 8.766 grams of sodium chloride you're going to add are not actually going to contribute any volume to your solution. And then you would just, after you've added the sodium chloride, you would just then bring the volume up to 1 liter. But in other cases, with other things that you might want to dissolve, things like Heaps buffer, Tris buffer, LB, LB media, a lot of other things, you don't want to assume that what you're dissolving will not take up any volume. So in those cases, you need to account for the volume that they're going to take up. So when you prepare the solution, the buffer, or the media, in these examples, if you're preparing 1 liter of each, you might only fill it up to 800 mils, and maybe you need to add 40 grams of something, and you then bring it up to a liter. So the take-home message is, you never fill up your solution when preparing it all the way to the final volume before you've added all the other ingredients. You fill it up to 70-80%, assuming that's going to account for the volume that that you're going to add with all the things you're going to dissolve. And sometimes you'll fill up to only 30 or 40%. So always make sure to account for, or think about whether or not you need to account for the volume of the things that you're going to dissolve in your solvent. So that brings us to percent solutions. Percent solutions are a very common way of preparing solutions. Let's actually bring this down a little bit. One way to calculate this is percent concentration times volume needed. Oops. This is a pretty often very simple way of calculating a solution preparation. So a very common is 70% ethanol. This is used in the lab for cleaning all the time. So the way that you would do this is pretty straightforward. Let's say that we want to prepare 500 milliliters of 70% ethanol. So all you really need to do is you multiply 500 milliliters by 0.7. Oops. So 500 mils times 0.7 is just 350 mils. So that means if we need to prepare a 70% ethanol solution, 500 mils of it, 350 mils have to be ethanol, and the remaining 150 would be water. This is also sometimes pretty common with buffers. For example, a destaining buffer that I've used quite frequently is made up of 20% methanol and 10% acetic acid. So often, because of the container I prepare it in, I prepare 4 liters of it at a time. So if I needed 4 liters of this solution, it's pretty straightforward. I can just multiply my volume needed times 0.2, and in this case gives me 800 mils of methanol. And then 4 liters times 0.1, and I get 400 mils of acetic acid. And then the rest of it's just water. So I've got 1200 mils total of methanol and acetic acid, or 1.2 liters. And then I just have the remaining bit, the 2.8 liters that's left, or 2,800 mils, is just water. So it's pretty straightforward when you're calculating percent solutions. Usually these are not very complicated calculations.
Okay guys, so really quick, I'm going to go over the Henderson-Hasselbalch equation. Really, this is more of a plug and chug. If you want more detailed information on this equation, which I suggest you might want, go on YouTube, find other videos. If you want, go into the modules on the week that we taught lab math, and there will be an extensive amount of information on the Henderson-Hasselbalch equation. But for our purposes now as a review, the Henderson-Hasselbalch is used to define the derivation of pH, buffer pH, equilibrium pH, and isoelectric point of proteins. So here's the Henderson-Hasselbalch equation. pH equals the pKa plus the log base 10 of the dissociated base over the weak acid. So how do you remember that it's A over HA? Well, you can just think of aha. It's not ha-ah, it's aha. I know it sounds silly, but works for me. So, it's really just a plug and chug. Whatever the question gives you, you find the missing variable. There's one thing, though, that's very important to realize, and that's that when the pH equals the pKa, the concentration of the acid is going to equal the concentration of the base. Well, how does that happen? Let's take a look at this formula. Copy, paste. When we look here, when we look here, the acid over the base. So if this is, let's make it simple. If this is 1 over 1, that's going to equal 1. The log base 10 of 1 is 0, so that's going to equal pH equals pKa. This is very important in a lot of your calculations. Other than that, just remember that the Henderson-Hasselbalch equation is derived from the acid dissociation constant. So just remember that when you're looking at this, HA will dissociate into H plus and A minus. Here though, it never really exists as just H plus. It's usually as a hydronium ion in most cases. Alright, so two fairly simple questions using the Henderson-Hasselbalch. First one, buffer of 1 molar acetic acid and 1 molar sodium acetate. What is the pH? I reminded you of the Henderson-Hasselbalch equation. This is a plug and chug, but wait, you notice that there's the same concentration of acid to base. So what does that do? That knocks off this whole part of the formula, leaving you with only pH equals to pKa. Now, you look and your teacher or professor has also given you the Ka. That is wonderful, but it's the Ka, not the pKa. So to get this, we need the negative log of 1.77 times 10 to the negative fifth, which is going to give me 4.752. That's just the calculator plug. Once we have this, pH is equal to that, so your final answer, the pH of the buffer with 1 molar acetic acid and 1 molar sodium acetate is equal to 4.752. Now that was an easy one. Let's get a little more detail. Alright guys, so now looking at a buffer of 0.8 molar acetic acid and 1 molar sodium acetate, what is the pH? So I reminded you of the Henderson-Hasselbalch equation again. And here we're just going to plug and chug. Luckily, from last time, we already have the Ka of acetic acid. We converted it into the pKa, which will give us, this right here is going to be 4.752. So now we have the log plus the log base 10 of aha. So that's actually going to be 1 over 0.8 because we have the dissociated base and the weak acid. Alright. So we plug this in. We're just going to get 0.097. And we add that to 4.752. We are going to get 4.849. So that is, so the answer is the pH of a buffer of 1 molar acetic acid and 1 molar sodium acetate will be 4